February 3rd, 1943. A Telefunken engineer named Brandt stood in a Berlin conference room, staring at twisted metal and burned circuit boards spread across a table. 2 weeks earlier, a British Sterling bomber had gone down near Rotterdam. Carrying equipment the Germans codenamed the Rotterdam Gerät, Brandt's team had spent 14 days examining every component, measuring every frequency, testing every circuit. Now, in this first meeting of the Arbeitsgemeinschaft Rotterdam, the Rotterdam Working Group, he had to deliver his assessment. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you're watching from today. The room held Germany's finest radar engineers, men who'd designed the Würzburg, who'd built the Freya network, who understood radio waves and electromagnetic propagation better than almost anyone alive. They expected Brandt to confirm what German intelligence had been saying for months. British radar was competent but unexceptional. German technology remained superior. Brandt opened his report. The captured device operated at 9 centimeters wavelength. It used a cavity magnetron, producing kilowatts of pulse power. It provided a complete map of the ground beneath the aircraft, displayed on a cathode ray tube, allowing bombers to navigate and attack through cloud, through darkness, through any weather. The British had miniaturized components German engineers thought impossible to shrink. They'd solved cooling problems German labs were still studying. They'd created a production radar using technologies Germany had abandoned as impractical. One of the senior engineers interrupted. "How many of these sets did the British have?" Brandt consulted his intelligence brief. Initial estimates suggested hundreds, possibly more than 1,000 sets already deployed. The engineer's face went pale. Germany had been working on centimetric radar for 3 years. They had prototypes. They had laboratory models. They had exactly 0 operational systems. But the Rotterdam device wasn't the worst news in Brandt's report. The magnetron itself, the heart of the system, bore markings that made several engineers lean forward. It wasn't British. The manufacturing codes indicated American production, Western Electric Company, Massachusetts. The British had invented the cavity magnetron. The Americans had turned it into something that could be mass-produced. Brandt continued reading. The quality of manufacture was extraordinary. Precision machining, consistent tolerances, interchangeable parts designed for high-volume production. This wasn't a hand-built prototype. This was an industrial product, built to a standard that suggested the Allies could produce these by the thousands. The engineer, who'd asked about quantities, looked at his colleagues. His voice was quiet when he spoke. "We're not competing with British laboratories anymore. We're competing with American factories." The meeting lasted 6 hours. They examined the magnetron under microscopes. They tested the receiver circuits. They measured the antenna characteristics. The display system alone represented years of German research compressed into a working design. The modulator pushed vacuum tubes to power levels German engineers had thought required larger, heavier components. The waveguide connections, the thermal management, the electrical isolation. Every aspect showed refinement that came from extensive development and testing. Near the end of the session, someone raised the obvious question: could Germany copy this? Brandt's answer was careful. Technically, yes. Given 2 years and unlimited resources, German industry could probably manufacture something similar, but 2 years assumed no Allied interference, no bombing of factories, no shortages of critical materials. 2 years assumed Germany had 2 years to spare. The Reich was fighting in Stalingrad. Rommel had been driven back in North Africa. Allied bombers struck German cities nightly, and now this evidence that the enemy possessed radar technology Germany couldn't match and manufacturing capacity Germany couldn't equal. The gap wasn't just technical, it was industrial. It was the difference between scientific understanding and production engineering, between laboratory prototypes and assembly lines. Brandt's final assessment was stark. The Rotterdam device confirmed that Allied radar development had overtaken Germany's. More critically, Allied production capacity was operating at a scale Germany couldn't hope to achieve. The British and Americans weren't just ahead in research, they were ahead in implementation, in manufacturing, in the systematic application of technology to warfare. The meeting ended with assignments. Copy the magnetron, study the display, understand the modulator, create countermeasures, begin crash programs to develop German centimetric radars. But everyone in the room understood the reality. They were catching up to a target that kept accelerating away. What Brandt didn't know, what none of them knew, was that the Rotterdam device represented just one system from one laboratory. Across the Atlantic, at the Massachusetts Institute of Technology, an organization called the Radiation Laboratory employed nearly 4,000 people. They worked in a sprawling complex that had grown from a few rooms to 15 acres of laboratory space. They'd developed not one centimetric radar, but dozens of different systems. Airborne intercept radars, naval search radars, ground mapping radars, fire control systems, submarine detection equipment, and they were designing new systems faster than Germany could even catalogue what existed. While German engineers studied the Rotterdam device, MIT researchers were already testing improved versions, while Brandt's team tried to copy the 9-centimeter magnetron. American factories were producing magnetrons by the thousands, shipping them to installations around the world. The story of how German engineers discovered this disparity is not about a single captured radar. It's about the moment when Germany's technical leadership realized they were losing the technological war. Not slowly, not marginally, but comprehensively. It's about highly competent engineers confronting evidence that competence wasn't enough, that they faced an opponent who'd turned radar from a scientific instrument into an industrial product, who'd mobilized research and production on a scale Germany couldn't match. It's about the collapse of assumptions, the shock of recognition, and the desperate scramble to close a gap that only grew wider with time. The Rotterdam Jarret represented more than captured equipment. It represented a revelation, and that revelation would reshape German radar development for the remainder of the war. October 1940, 18 months before Rotterdam. In a building at MIT's campus in Cambridge, Massachusetts, a group of physicists gathered for the first time. None were radar specialists. Most had spent their careers studying cosmic rays, nuclear physics, theoretical problems far removed from military hardware. They'd been pulled from universities across America, Columbia, Berkeley, Stanford, Chicago, with promises of important war work. Their leader was Lee Dubridge, a nuclear physicist from Rochester. His deputy was Isidor Rabi, who would later win the Nobel Prize. They'd been assembled to solve a problem. British radar was effective, but operated at long wavelengths. Shorter wavelengths would provide better resolution, allow smaller antennas, enable new applications. But generating sufficient microwave power seemed impossible. Then, the British arrived with a gift. The Tizard mission, a delegation of scientists sent by Churchill to share technology with America, brought a device the size of a hockey puck, the cavity magnetron. It generated microwave power at levels that stunned American engineers. 10 kilowatts of pulsed power at 10-centimeter wavelength, 100 times more powerful than anything American labs had produced. The demonstration at RCA laboratories had left engineers speechless. This single device opened possibilities that had seemed years away. Airborne radar with resolution sharp enough to see individual buildings, naval search radar that could spot submarine periscopes, fire control systems accurate enough to guide anti-aircraft guns without searchlights. The MIT Radiation Laboratory, quickly nicknamed the Rad Lab, started with 4,000 square feet and $500,000 in funding. It would grow into something unprecedented in the history of science. The name itself was deliberately misleading. Radiation Laboratory suggested nuclear physics, abstract research, unlikely to interest enemy intelligence. In reality, from day one, the Rad Lab focused on one goal: transform the cavity magnetron into operational radar systems. The organization that emerged was Revolutionary. Unlike traditional research labs, the RAD lab mixed physicists, engineers, and military officers in the same building. Unlike traditional military development, it gave scientists enormous freedom to pursue promising ideas. Unlike traditional academic research, it demanded working prototypes, not papers, field testing, not theory. Money flowed without normal restrictions. By 1941, the RAD lab received essentially unlimited funding from the Office of Scientific Research and Development. Want to test a new antenna design? Order the equipment. Think you can improve the magnetron? Build it. Need field trials? The military will provide aircraft, ships, personnel, whatever's required. This approach violated every rule of peacetime research. No peer review, no grants committee, no competitive funding process, just urgency, resources, and brilliant people turned loose on critical problems. The results were extraordinary. Within 6 months, the RAD lab developed the first microwave airborne intercept radar. Within a year, they'd created air-to-surface vessel radar that could spot submarines. Within 18 months, they'd designed fire control radars accurate enough to guide guns onto nighttime targets. Each new system spawned variations, naval versions, airborne versions, ground-based versions. Each variation revealed new problems, which triggered new research, which led to new solutions. The RAD lab didn't work in isolation. They partnered with industry from the start. Bell Labs contributed communications expertise. RCA provided manufacturing knowledge. Western Electric scaled up production. Raytheon, Sylvania, General Electric. America's radio and electronics companies turned MIT designs into production hardware. This integration of research and manufacturing was something Germany never achieved. German radar development was compartmentalized. Telefunken worked on one system. Lorenz worked on another. Gamer handled naval radars. The Luftwaffe's Signal Corps controlled research priorities. University scientists pursued theoretical questions. The connections between research, development, and production remained tenuous. America approached the problem differently. The RAD lab designed systems with manufacturing in mind. They used components industry could produce. They tested prototypes in the field, incorporating feedback from operators. When production began, engineers from the RAD lab worked alongside factory staff, solving problems in real time. By late 1941, when Germany still operated maybe 200 radar sets, mostly Freya early warning systems and Würzburg gun-laying radars, American factories were ramping up production of multiple radar types. The exact numbers from this period remain uncertain, but the trajectory was clear. German radar development proceeded carefully, thoroughly, in limited numbers. American radar development moved with industrial speed, accepting good enough solutions in exchange for quantity and diversity. The difference in philosophy ran deep. German engineers pursued technical perfection. Each Würzburg was precision-built, carefully tested, a triumph of radio engineering. The parabolic dish was machined to exacting standards. The circuits were hand-assembled by skilled technicians. Quality control was rigorous. Production was slow. American engineers pursued practical effectiveness. MIT designed radars that worked well enough to change battlefield outcomes. Western Electric built them using mass production techniques borrowed from telephone manufacturing. The sets weren't perfect. Early models had reliability problems. Field modifications were constant, but they got to the field fast, in large numbers, and evolution happened through rapid iteration rather than prolonged development. Consider the SCR-584 anti-aircraft radar. The RAD lab started design work in February 1941. The first experimental model was tested in August 1941. Production began in April 1942. By D-Day, in June 1944, more than 1,500 sets were deployed, less than 3 years from concept to battlefield deployment at scale. This was the kind of development cycle Germany couldn't match, or the H2S ground mapping radar. British scientists invented the concept. The RAD lab improved it, creating the H2X version with 3 centimeter wavelength for sharper images. From the captured Rotterdam device in February 1943 to American H2X deployment in October 1943. 8 months. Germany spent those same 8 months trying to understand how the British magnetron worked. The production statistics tell the story clearly. By war's end, manufacturers produced radar systems from MIT designs worth more than $1.5 billion, over 100 different radar types, tens of thousands of individual sets deployed on ships, aircraft, ground installations across every theater of war. Germany produced excellent radars. The Würzburg was sophisticated, accurate, well-engineered. Between 3,000 and 4,000 sets were built during the entire war. The Freya was robust and reliable. About 1,000 units were manufactured. These were Germany's primary radar systems, 4,000 to 5,000 sets total, representing years of development by highly skilled engineers working in some of the world's most advanced electronics laboratories. Against this, America deployed tens of thousands of radar sets designed in less time, manufactured faster, updated constantly, with field improvements. The disparity wasn't subtle, it was overwhelming. And in February 1943, when Brandt examined the Rotterdam device in Berlin, this disparity suddenly became visible to German engineers who'd assumed their side maintained technical parity. Part 2 of the script. The shock of the Rotterdam device rippled through German radar development like a seismic wave. Within days of that first meeting on February 22, 1943, the Arbeitsgemeinschaft Rotterdam became one of the highest priority technical programs in the Reich. Brandt's committee met weekly, sometimes more frequently, coordinating efforts across Germany's fractured radar establishment. The meeting minutes reveal the scope of the challenge. March 8, 1943. Discussion of magnetron reproduction. Telefunken reported progress copying the British cavity design, but production magnetrons showed inconsistent output. Peak power varied by 30% between units. The British original they were copying had been manufactured to tolerances German tube makers struggled to achieve. American manufacturing standards, it seemed, exceeded what Germany's precision engineering could match economically at scale. March 17, 1943. Report on centimetric receiver technology. Lorenz had developed detector crystals that worked, but with higher noise figures than the British design. The waveguide components required machining accuracy that only a few German shops could provide. Scaling production would take months, possibly years. Someone asked about American manufacturing capacity for these components. The intelligence assessment was grim. Americans were producing waveguide components on turret lathes using semi-skilled labor in quantities Germany couldn't approach. April 8, 1943. Discussion of display technology. The British cathode ray tube in the Rotterdam device used a long persistence phosphor that left a fading trace, allowing operators to see ground features building up with each radar sweep. German tube manufacturers produced similar phosphors, but the brightness and persistence characteristics didn't match. Again, American industrial chemistry exceeded German capabilities. The committee authorized research into alternative display methods while continuing efforts to copy the British approach. By summer 1943, the Rotterdam Working Group had assembled a functioning copy of the H2S radar. Sort of. It worked in the laboratory. It produced images of the surrounding terrain when mounted on a test tower, but it wasn't ready for production. Too many components required hand-fitting. Too many circuits needed individual adjustment. The British original was designed for manufacture. The German copy was a reverse-engineered approximation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. More disturbing were the intelligence reports arriving from other sources. The Rotterdam device wasn't unique. Similar British H2S radars had been captured in other crashed bombers, and American bombers were now appearing over Europe with a different ground mapping radar operating at 3-centimeter wavelength. The H2X, even more advanced than the 9-centimeter British system, sharper images, better resolution, and clearly manufactured in quantity based on the number of equipped aircraft. German engineers did the calculations. The progression from 10-centimeter wavelength to 9 centimeters to 3 centimeters represented a massive increase in complexity. Magnetrons had to operate at higher frequencies. Waveguides became smaller, requiring tighter tolerances. Antenna dishes needed finer surface accuracy. Each step up in frequency multiplied the engineering challenges. Germany was still trying to copy a 9-centimeter radar the British had deployed in early 1943. The Americans were already fielding 3-centimeter radars in late 1943. The gap wasn't closing, it was widening. General Wolfgang Martini, head of the Luftwaffe's Signals Intelligence Service, read the Rotterdam Working Group reports with growing concern. Martini was one of the few German officers who truly understood electronics. He'd warned about British radar before the war. He'd pushed for German radar development throughout the conflict. Now he faced evidence that his warnings had been insufficient. In a classified memo dated November 1943, Martini outlined the situation. German radar technology was qualitatively good, but quantitatively inadequate. The Würzburg and Freya systems were well designed, but produced in numbers too small to provide comprehensive coverage. German centimetric radar development was progressing, but remained years behind Allied operational systems. Most critically, German radar production capacity was perhaps 1/10 of Allied capacity. That final point was the killer. Even if German engineers could match Allied designs, German factories couldn't match Allied production. The Reich lacked the industrial base, the manufacturing expertise, the raw materials, and increasingly the electrical power to run factories at full capacity. Allied bombing was destroying production facilities faster than they could be rebuilt or relocated. The contrast with American operations was stark. While German engineers labored to copy the Rotterdam device, the MIT radiation laboratory was expanding. By mid-1943, the RAD lab employed 3,500 people. 20% of America's physicists worked there. The budget ran close to $4 million per month. 15 acres of laboratory space hummed with activity. Teams working on airborne intercept radar coordinated with teams developing naval search radar, who coordinated with teams creating gun-laying systems. The organizational structure itself was a weapon. Division 5 handled airborne systems. Division 6 handled naval systems. Division 8 handled fire control. Each division contained groups focused on specific problems: antennas, modulators, receivers, displays, and, crucially, each division maintained constant communication with the others. Antenna improvement developed for airborne radar might be adapted for naval use. A modulator breakthrough in fire control could improve search radar performance. This cross-pollination of ideas accelerated innovation in ways German compartmentalized research couldn't match. Telefunken didn't share developments with Lorenz. The Luftwaffe's radar work proceeded separately from Kriegsmarine programs. University research remained disconnected from military applications. Germany had brilliant scientists and excellent engineers, but they worked in isolation, solving problems that colleagues elsewhere might have already addressed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The RAD lab also maintained something Germany lacked: direct field testing feedback loops. When a new radar design was ready for trials, military officers stationed at the lab arranged immediate testing with operational units. Pilots flew the equipment in combat conditions. Naval crews operated it at sea. Anti-aircraft batteries used it to track targets. Within weeks, sometimes days, feedback returned to MIT. The equipment worked or it didn't. Problems were identified, solutions proposed, modifications implemented. This rapid iteration was possible because the RAD lab controlled the entire development process. They designed the system, they built the prototypes, they tested them in the field. When modifications were needed, they made them immediately without waiting for approval from distant bureaucracies. The laboratory operated with wartime urgency, but peacetime flexibility. A combination Germany's rigid military hierarchy couldn't replicate. Consider the development of the SCR-720 airborne search radar. Initial designs showed promise, but suffered from excessive weight, too heavy for fighter aircraft. The antenna group developed a new lightweight scanner. The modulator group reduced component count. The receiver group miniaturized circuits. Within 3 months, they'd cut system weight by 40%. Prototype testing revealed vibration problems. The mechanical group redesigned the mounting. Another month. Problem solved. By contrast, German radar modifications required approvals through layers of military and industrial bureaucracy. Changes that took MIT weeks took Germany months. The production advantages were equally stark. When the RAD lab finalized a design, they worked directly with manufacturers to set up production lines. Engineers from MIT would travel to RCA or Western Electric, spending weeks on the factory floor, solving manufacturing problems as they arose. This hands-on approach meant production radar actually worked, rather than requiring extensive field modifications. Germany attempted similar collaboration, but struggled with scale. Telefunken could produce perhaps 50 to 100 radar sets per month at peak capacity. Western Electric, leveraging techniques from telephone manufacturing, could produce hundreds of radar sets per month from a single plant, and America had multiple plants. The difference wasn't German incompetence, it was American industrial might applied to electronics manufacturing with unprecedented focus. By early 1944, the quantitative gap had become impossible to ignore. German intelligence estimated, conservatively, that the Allies had deployed more than 10,000 radar sets across all services and theaters, perhaps 15,000. Numbers varied by source, but all pointed to the same conclusion. Allied radar deployment exceeded German deployment by at least an order of magnitude, 10 to 1, possibly 20 to 1. For German commanders, this disparity manifested in combat effectiveness that couldn't be overcome through skill or courage. Allied bombers could navigate an attack through clouds that grounded Luftwaffe fighters. Allied naval forces detected U-boats before the submarines could spot convoys. Allied anti-aircraft batteries hit targets German flak crews could barely track. In every domain, radar multiplied Allied capabilities while German forces operated partially blind. The Würzburg radars Germany did possess were excellent for their purpose, gun-laying for anti-aircraft artillery, but there weren't enough of them. A typical German city might have 6 to 8 Würzburg radars covering approaches, not sufficient against raids of hundreds of bombers. Allied countermeasures, chaff, electronic jamming, saturation tactics, could overwhelm the limited number of German radar sets. More radars would have helped. Germany couldn't produce them fast enough. German engineers understood the problem clearly. In a technical assessment written in April 1944, a Telefunken engineer named Heinrich Rothe analyzed Allied radar production. His conclusions were damning. The Allies had transformed radar from precision military equipment to industrial commodity. They accepted lower performance standards in exchange for quantity. They designed for manufacturability rather than optimal engineering. They iterated rapidly rather than perfecting slowly. And this approach, which violated German engineering principles, was winning the war. Rothe's analysis identified the fundamental mismatch. German culture valued precision, craftsmanship, perfectionism. The Würzburg was a beautiful piece of engineering, accurate, reliable, sophisticated. But making each one required skilled labor, time and resources Germany couldn't spare. American culture valued pragmatism, speed, sufficiency. The SCR-584 was good enough, functional, adequate, effective, But making thousands of them required only semi-skilled labor, standardized components, and industrial processes America had perfected during decades of mass production. Neither approach was wrong in absolute terms, but in the context of total war, American pragmatism delivered superior results. 100 radars that worked adequately beat 10 radars that worked perfectly, especially when the 100 could be built in the time needed to build the 10. By mid-1944, Germany attempted to accelerate radar production through emergency measures. Factories were ordered to prioritize radar components. Labor was diverted from other programs. Resources were allocated at higher priority. Production increased from perhaps 150 radar sets per month across all types to maybe 300 per month by late 1944, an impressive doubling of output. During the same period, American radar production continued expanding. MIT designed new systems. Factories increased capacity. By 1945, American manufacturers were producing thousands of radar sets per month. The absolute numbers remain uncertain, but the ratio was overwhelming. Germany's maximum production surge still left them outnumbered 10 to 1, perhaps 15 to 1. The Rotterdam Working Group continued meeting throughout 1944, growing increasingly desperate. They developed the Berlin radar, Germany's first operational centimetric system, using knowledge gained from the captured H2S. The Berlin radar worked. It performed well in testing. About 100 to 150 sets were eventually produced. American factories were building H2X radars by the thousands. The Berlin radar actually demonstrated impressive German engineering. Despite being reverse-engineered from captured equipment, despite lacking American manufacturing resources, despite operating under constant Allied bombing, German engineers created a functional 9-centimeter radar in roughly 18 months. Under peacetime conditions, this would have been an achievement worth celebrating. But the war wasn't waiting. By the time Berlin radars entered service in early 1945, the Allies had moved on to more advanced systems. The 3-centimeter wavelength was standard for new American designs. Research was underway on even shorter wavelengths. Germany was still catching up to where the Allies had been in 1943. In some ways, the Berlin radar represented the tragedy of German radar development. Highly competent engineers working with limited resources under impossible conditions achieved something remarkable. And it wasn't enough, would never be enough. Because the problem wasn't German capability, it was German capacity. And capacity required industrial infrastructure Germany no longer possessed. The bombing raids that struck German cities also destroyed radar factories. Telefunken's Berlin facilities were hit repeatedly. Lawrence plants in Stuttgart suffered damage. Even when production equipment survived, transportation networks failed. Components made in one city couldn't reach assembly plants in another. Workers couldn't get to factories. Electrical power became unreliable. The entire system that sustained high-technology manufacturing was disintegrating. Meanwhile, American factories operated in safety, thousands of miles from combat, 3 shifts per day, 7 days per week. Components flowed from specialized manufacturers to assembly plants on intact railroads. Electricity was abundant. Labor was available. The MIT Rad Lab designed improvements that factories implemented within weeks. The cycle of innovation and production proceeded without interruption. By late 1944, German radar engineers were designing systems they knew couldn't be built in meaningful quantities. The Bremen radar, an advanced 3-centimeter design, reached prototype stage. Perhaps a handful were constructed. The Neptune series of airborne intercept radars showed promise. Limited production run. The Corfu receiver for detecting Allied radar. Shortage of components prevented widespread deployment. The technical reports from this period make painful reading. German engineers documenting systems that would have been effective if only they could be manufactured. Designs that solved problems if only resources existed to implement them. Innovations that could have countered Allied advantages if only time and industrial capacity permitted. The gap between German engineering capability and German industrial reality had become unbridgeable. May 1945. The war in Europe ended with Germany's surrender. Allied technical intelligence teams fanned out across the collapsed Reich, searching for advanced weapons, secret research, hidden technologies. They found rocket facilities at Peenemünde, jet aircraft prototypes, experimental tanks, and they found radar installations, Würzburg dishes pointing at empty skies, Freya arrays that would never detect another raid, Berlin radars that had barely seen service. The technical assessments written in the war's aftermath told a story the Germans had already understood. German radar technology was qualitatively excellent. The Würzburg's accuracy impressed Allied engineers. The Freya's robust design earned respect. The Berlin radar, reverse-engineered under impossible conditions, demonstrated remarkable engineering skill, but quality couldn't overcome quantity. Sophistication couldn't defeat industrial scale. American engineers who examined German radar facilities noted the careful craftsmanship, the precision assembly, the attention to detail. They also noted the production numbers, 3,000 to 4,000 Würzburgs over 5 years of war. Perhaps 1,000 Freya systems, a few hundred other types, total German radar production. Maybe 5,000 sets, across all variants, all purposes, all services. The MIT Radiation Laboratory alone had designed systems worth over $1.5 billion in production contracts, tens of thousands of individual radar sets, 100 different system types. Half of all radar deployed by American forces originated from MIT designs. And that didn't count British production, Canadian manufacturing, or American systems developed by the Naval Research Laboratory and Signal Corps. The final accounting was brutal. Allied radar deployment exceeded German deployment by factors of 10, 15, possibly 20 to 1. The exact ratio would never be known with certainty, but the order of magnitude was clear. Germany had been comprehensively outproduced, outdeployed, out-innovated in one of the war's most critical technologies. Heinrich Rothe, the Telefunken engineer who'd analyzed Allied production in 1944, was interviewed by American intelligence officers in June 1945. They asked him when he'd realized Germany would lose the technology race. Rothe thought carefully before answering. He said the moment of recognition came when he studied the Rotterdam device's magnetron, not because the design was revolutionary, because the manufacturing quality was routine. This extraordinary piece of technology had been built to standards that suggested mass production was straightforward. That's when he knew the Allies hadn't just developed advanced radar, they'd industrialized it. The interviewer asked about German countermeasures, the Berlin radar, the crash programs to close the gap. Rothe's response was honest. German engineers could design equivalent systems. They understood the principles. They possessed the scientific knowledge. What they lacked was industrial capacity operating at American scale. You can't engineer your way out of a production disadvantage measured in orders of magnitude. Skills matter, but factories matter more. Wolfgang Martini, the Luftwaffe signals intelligence general who'd warned about British radar in 1939, survived the war. In 1947, he gave testimony about German radar development for Allied investigators compiling technical histories. Martini spoke about the intelligence reports crossing his desk throughout the war, the captured equipment that revealed Allied advances, the prisoner interrogations describing radar systems Germany didn't possess, the photographic reconnaissance showing antenna arrays at numbers Germany couldn't match. The investigators asked if better intelligence earlier in the war would have changed outcomes. Martini smiled, a tired expression. Better intelligence wouldn't have created more factories. It wouldn't have provided resources Germany didn't have. It wouldn't have protected production facilities from bombing. Germany knew about Allied radar advantages. Knowledge wasn't the problem. Capacity was the problem. The story of German engineers examining American radar is ultimately about the limits of excellence without scale. About the moment when highly skilled people realized that competence wasn't enough, that they faced an opponent who'd transformed technology into industrial production, who'd mobilized manufacturing capacity Germany couldn't equal. When Brandt first opened that Rotterdam working group meeting in February 1943, examining twisted metal from a crashed bomber, he'd known immediately The quality of manufacture told him everything. The precision of the components revealed the truth. Germany was competing not against British laboratories, but against American industry. And that was a competition Germany had already lost. The engineers who examined the Rotterdam device were right to be shocked. They were right to scramble, to copy, to try, closing the gap. But they were attempting to bridge a chasm with tools designed for gaps. American factories were producing thousands of radar sets. Germany managed hundreds. The mathematics of that disparity were unforgiving. Excellence couldn't overcome scale. Precision couldn't defeat quantity. And the recognition of that reality in a Berlin conference room in February 1943 marked the moment German engineers understood they were losing a war measured in production capacity, not technical sophistication. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.